Well, I hope everybody had a good Thanksgiving. We're going to move on to 10.3 and 10.4. This is going to be titled Matrices. Matrix, matrices, etc. The matrices is the plural version of matrix. So, what is a matrix in mathematics? Mathematics, it's very simple. We give it meaning, but all it is a matrix is an array of numbers. The word array just means a box of. It's a box full of numbers. Now, even though it's just a box full of numbers, we give it meaning so that we can have some uses with it. So, in particular, these are going to be for, we are going to use for linear system. Use for linear system. They have other applications without thinking about linear systems, but in particular, we will view them as linear systems. They make it a very good, or they make our problems very organized so that when we're doing our work, we don't have to keep track of all the variables that are hanging around into our problem. So, let's take a simple one real quick. Let's take the linear system example. Let's take the linear system, let's see, what's that? 2x plus y minus 2z. And you guys might have remembered this from the last one. Negative x minus 1/2 y plus z equals negative 6. 3x plus 3/2 y minus 3z equals 18. To turn this into an array, turn this into a matrix, we're going to have something called an augment matrix. It's a special type of matrix, special type of box of number where each of the coefficients of our variables, there are 3 variables over here, we're going to write down each of the coefficients: 2, 1, negative 2, negative 1, negative 1/2, 1. If there's no variable in that equation, but we still have it in our system, then we treat it as a 0. And this is 3, 3/2, negative 3. These are going to represent the coefficient of systems. And then your last column, that's going to represent the constant. This is why we call it augmented. It's augmented when the last column will refer to whatever our constant is equal to. Oops, I don't need an equal sign. Negative 6, 18. This is our array of numbers, or our box numbers. Boom. You have this column in particular. This is going to be your constants. And this is going to be your coefficients. This is what's going to make up our actual matrix or matrices. Now, in particular, you need to know terminologies with these matrices. In this case, we call this a 3/4 matrix. This is known as the dimension / size of matrix. And it is always going to be in terms of row versus your column. We have 3 rows in our matrix, and then in particular we have 4 columns. So we call it a 3/4. So again, all I did was for my system, I wrote down all of its coefficients, and I wrote down the last column as the constant part where my system is equal to. And then I arrange it inside this box and whatnot. Now, our rules for Gauss elimination, when we use Gauss elimination to solve for this, will apply for our augmented matrix. Because all these are just representations of our numbers without the variables themselves, we can still have the same operation that we have worked with. So we can use Gauss elimination. So if I were to do Gauss elimination on this guy right here, Gauss, if you recall, let's see if I have it. Well, I have it on this page. We did the Gauss elimination over here. Boom. This is the exact same system that we did last time. But when I did Gauss elimination, I had this system right here. Oops. Let's do it right here. Sorry. If I were to write this as a matrix, we have 1, 1/2, negative 1, 6. 1, 1/2, negative 1, 6. This turns into 1, 1/2, negative 1, 6. And then our other rows, 6, negative 1, 6. Our other rows is going to be a row 0 equals 0. So these are going to be zeros for each of these equations. Each of these rows will be a row of zeros because we have 0 equals zeros. That means each of the variable has a coefficient of 0 because they did not appear in our line. This is what happens when we have Gauss elimination. Now, it's important that we understand what we're trying to do once we have it triangularized. We talked about triangularizing the system. How does that look in particular with Gauss elimination or with matrices? Well, it turns out if we do triangularization, we have something called row echelon form. This is triangularization with leading entry 1. So the entire time we did triangularization, we've always left it, I've told you guys to leave it with the coefficient of 1 for each of the variables. Well, it turns out that's something called row echelon form in the matrix world. So in particular, we need to satisfy 3 conditions to be in row echelon form. Row echelon form states that we need to have the first non-zero entry of each row is 1. This is called leading entry. Oops. Not the 1, but whatever it is, we call that the leading entry. I used that word earlier, now we know what it means. It just means the first number that appears in our row that is not 0. In this case, our leading entry over here is 1 for the first row. We do not have a leading entry in row 2 or row 3 in our matrix after we perform Gauss elimination. However, over here we have 2, negative 1, 3. Not as helpful, but those are our leading entries, which they need to be 1 to be in row echelon form. And that's what happens when we triangularize it. Second thing that you need to have if you want it to be row and echelon form, the leading entry in each row is to the right of the leading entry in the row above it. The leading entry in each row is to the right of the leading entry in the row above it. So, as I'm reading downwards over here, so this is not a good example, so I'll make an example in a bit, but as I'm reading downwards on my matrix, then every leading entry should be to the right of it. It'll kind of make this diagonal / staircase pattern. And the final one is the easiest property. Sometimes you don't even have to worry about it because sometimes we don't have it. All row of zeros are at the bottom of matrix. All rows of zeros are at the very bottom. If you have all of these conditions satisfied, that means your matrix is in something called row echelon form. And again, we have always actually put things in row echelon form when we triangularize it, as long as your coefficient is 1. If you triangularize and turn all your leading coefficients to 1, you automatically have row echelon form. Example. Let's suppose I have 3, oops, I'm sorry. 1, 3, 2, 4, 0, 1, 3, 8, and 0, 0, 1, 2. This matrix right here, this is in row echelon form. Why is it in row echelon form? This is the acronym. Why is it in row echelon form? Well, the leading entry here is 1, the leading entry here is 1, leading entry here is 1. We cannot consider 0 as a leading entry. There are no row of full of 0, so this is already satisfied. Moreover, each of these leading entry 1, if I were to go look to the next one from here to here, notice that as I'm going down the rows, it's going to the right. So I'm going to the right, and that's where my next leading entry is. Down to the right, and that's where my next leading entry is. So this is row echelon form. An example of one that is not row echelon form, you might have something like this. This right here is not row echelon form. So I should capitalize the letter because it's an acronym. Why is this not row echelon form? Even though these are all 1s, the leading entries are 1s, and I have the row of zeros at the very bottom, the second row leading entry is not to the right of the first row's leading entry. So this is not row echelon form. And the final example I'll give you is this. This right here. In this particular case, we have leading entry over here. We have 2 of the leading entries. Now, this system might not be consistent, but is it in row echelon form? Yes, it is in row echelon form. Even though they're not adjacent to each other, the leading terms, because I jumped over 1 to the right, or 2 to the right, I guess, in this case. It is still to the right of the leading entry from this entry over here. So as I'm reading it from top row to bottom row, they are moving to the right. So this is in row echelon form. Boom. All right. And then just as a little heads up, the first matrix we have over here, this is a 3x4. We say this is 3x4. We say this one right here is also a 3x4. And then we say this one right here is a 2x3. Rows versus their columns. That's how we define their size / dimension. So, every time we had triangularized this system over here, we've always had it in row echelon form. We call it triangularization, but if I just turn the coefficients to 1, then it is row echelon form in the matrix world. So that's very helpful. Well, that's nice. And then let's in particular talk about one extra condition. So these 3 make up row echelon form. Well, there's a 4th one actually. that is not part of, well, let's see. Fourth one right here, I'll just state in particular, it's an add-on to your properties where, I'm going to cut this off. This is going to be reduce row echelon form. This is a stronger version. If I were to have a fraction, think of this as fully simplifying your fraction down to as much as possible. This last property states that, hey, to be in reduced row echelon form, you need the first three, but additionally, you need to have each leading entry has only zeros above and below it. Every time I have a leading entry, the only numbers that can be above and below it have to be 0. So if we look at this case right here, over here, this leading entry is 1. Below that are all zeros. If I look to my next leading entry over here, above that is a 3 and below that is a 0. Automatically, it is not in reduced row echelon form. An example of reduced row echelon form we have is this one right here. I have a leading entry 1. Below it are all zeros. Above it, there's nothing. But that is the only leading entry, so all of the leading entries have only zeros above and below it. Meaning, in your column that consists of your leading entry, you should only have zeros outside of your leading entry. So, let's identify if they're in row echelon form, reduced row echelon form, or neither. Let's identify that real quick. Let's suppose I had these matrices. 0, oops. -1/2. I believe that's a 1/2. 0, 6, 1, 0, 3, 4, -5, 0, 0, 0, 1.4, 0, 0, oops, 0, 1, 1, 0, 0. This matrix, and then let's do the next matrix. Zero, 0, 1, 1/2, and 0, 0, 0, 0, 0. All right, so I have these three matrices. Go ahead, take your time, pause the video, see if you can identify which one is in row echelon form, reduced row echelon form, and which one is neither. So I'll give you guys time. Go ahead and pause the video. All right, if you had tried it out, you'll notice that the first one is neither. Reason why is because your leading entry here, you have a leading entry here, you have a leading entry here, you have a leading entry here. Now, fortunately, all of these leading entries are 1s. We do not have a row of 0, so those two are checked off the box, but they are not to the right of each other as I progress down my rows. The first row is at the second column, but then the second row is in the first column, so I'm moving to the left. That means it is not in row echelon form. And if it's not in row echelon form, it's definitely not in reduced row echelon form. Let's look at the second one. Where are your leading entries located at? Your leading entries are located right here, 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 and that's it. So we have 3 leading entries. They are all 1s, so that's good to go. Now, our row of zeros are all at the very bottom. Yes, my row of zeros are at the bottom. And these are all to the right of each other. So it is in row echelon form. This is in row echelon form. Is it reduced, however? Well, let's take this leading entry 1. Does it have all columns of zeros besides the leading entry? Yes. So this one is good to go. This one right here, unfortunately, above it is a -6 and not a 0. Automatically not reduce row echelon form. It's in row echelon form, but is not fully reduced. And then we look at our last candidate over here. And our last candidate, our leading entries are here, here, here. We do have a row of zeros at the very bottom. We do have our leading entries being only the value 1. And they are all to the right of each other as I progress down my rows. So this is row echelon form. Echelon form. Oops. Let me just erase this. This is in row echelon form. Now the question, is it reduced? Well, let's take each of the columns for the leading entry. In this column, the leading entry is 1. Well, above and below it are all zeros. There's nothing above it, and all below it there's 3 zeros, so it does check out. So this is good. Let's look at the next column. In our next column over here with the leading entry 1, we have above it zeros and below it 2 zeros. So this one is also good to go. And then our last leading entry over here, above and below it are all zeros. So this is also reduced row echelon form. And now, on the test, I will require you to know or to state which one is it specifically. So you do have to tell me it's reduced row echelon form. So we're good to go on that. And again, this is triangularization. It's just one of the triangularization is more simplified than the other, which is very nice. So this is a little nice practice to see if we can fully reduce, or can we identify if it's fully reduced, if it's in echelon form, or if it's not even reduced at all, or if it's not simplified at all. Now, why is this important? Well, reduce row echelon form is unique. Echelon form or row echelon form is not unique. What this means is that if two students were to do different ways of simplifying their matrix, but they have it in reduced row echelon form, as long as they did their math correctly, they should both have the same exact matrix. If two students were to just put it in row echelon form without having these columns with the leading entries being only zeros, two students might have different matrices. They both might be correct, but they might be different. So boom. So now I want to make sure that we are also understanding of how we can read these matrices and turn them into or understand how they relate with systems. So I told you how to go from system into matrices over here, from here to here. But can you go backwards? Are you able to replicate this idea backwards? So let's see if we can go backwards. Oops, you scroll down all the way. Matrix to system. And this is important. You do need to know how to go backwards, especially once you have done your Gauss elimination. So matrix to Gauss elimination. Let's see if we can just do one problem. We'll just do one, just to make sure we're on point with this. Let's do 1, 2, 0, 4, 3, 0, 1, 5, 6, 8, 0, 1, 2. Oops. You do this. You put in row echelon form. And the last one I'll just fix up into if we have something like this. Now, if I were to give you this matrix and I ask you to go into to put into linear system, like let's say you want to solve your system of equations. I don't know if this matrix work or not. However, the way you would do it is you would look at the last row in particular. This last row, or before you even look at the last row, you have to count how many variables you have. Remember, this last column you have is your constants. It's what your equations are equal to. Everything else are your variables. How many variables do you have? You have 1, 2, 3, 4 variables. 1, 2, 3, 4. So that means we have x or w, x, y, and z. Okay? The last row right here represents z equals 0. These are the coefficients. The coefficient of z is 1, and it's equal to the value 0. The row above it should represent, what is that? What's before z? It is y. So we have y plus 3z equals 2. And if I go above that, we have x plus 5y plus 6z equals 8. And then lastly, if I go above that, I have x, or not x, I'm sorry. We have w plus 2x plus 4z. There's a 0y, that means it's gone, equal to 3. That's what our system of equation looks like once we go from matrix to our systems of equation. And then I can solve for each of the variable parameterize, and find your solution. So I can do all that stuff. I don't know if this matrix works. I'm just giving you the example of how to go from matrix to linear system. So that's very important. Now, when we were doing Gauss elimination, so operations on matrices, when we were doing Gauss elimination, these are when we're doing Gauss elimination, I stated that, hey, we can interchange rows. We can add one row, one multiple or one scalar of one row to another, and I can scale a row by a non-zero constant. Those are my 3 rules. Well, they are the same with operations on matrices. We can, again, so if I want to do all my operations that I can do possible, I can interchange rows. And this is why I've kept calling it rows instead of equations, is because I look at them as matrices. I can also add a multiple, non-zero multiple of one row to another row. So you guys already have this right here. And then I can scale a row by a non-zero constant. Of course, I don't want to multiply it by 0. Otherwise, then it would just ruin the matrix themselves, because then you would just have a row full of zeros or a matrix full of zeros, and that gets us nowhere. All right, so your operations on matrix are the exact same as your Gauss elimination on your linear systems. So with that in mind, let's see if we can kind of do some problems real quick. Let's see, where's that? Sorry, I can see it. Let's try out let's do turn the system to row echelon form. Turn the system into row echelon form. X minus 2y plus 3z equals 1. X plus 2y minus z equals 13. 3x plus 2y minus 5z equals 3. This system right here. If I wanted to turn the system into row echelon form, first I must turn it into a matrix. So turning this guy into a matrix, you should have the coefficients being 1, negative 2, 3, 1, 1, 2, negative 1, 13, 3, 2, negative 5, 3. Boom. Now I can do all of my operation without worrying about the variables at face value. So the leading coefficient, if I want to turn this row echelon form, this has a leading coefficient of 1. So I'm happy about that. However, remember, your next leading coefficient has to be to the right of it. So that means this guy right here needs to be a 0. Oops, you guys can't see that. This needs to be a 0 somehow. So how do I turn that into a 0? Well, you should have multiplied row 1, negative row 1, I'm sorry, plus row 2, and you're going to send that to row 2. In doing so, I have 1, negative 2, or 3, 1. Nothing changed for the first row, but the second row, this is now gone. This is a 4. Negative 2 times negative 1. That's positive 2 plus 2 is 4. Yep. 3 times negative 1. That's negative 3 plus negative 1. That's negative 4. And then I have 1. That's negative 1 times, is it 13? Yeah, 13. Or added by 13. That becomes 12. Negative 5, 3. This is my new matrix right here. Now, in particular, your leading entry here is 4, 0, 1, and leading entry here is 4. So I need to turn that into a 1. How can I turn that leading entry to a 1 without changing this value 0? If I add it to another equation, that's not going to be a 0 anymore. Because if I add it to the first equation, then I'll have a 1 instead of a 0. I might have a 2 instead of a 0. So I need to do something to row 2 without affecting that first entry. And then you should have stated that you're going to actually scale this down by 1/4 of row 2. If you do that, you have 1, negative 2, 3, 1, 0, 1, negative 1, 3, 3, 2, negative 5, 3. So now this has a leading coefficient of 1. This has a leading coefficient of 1. We're almost there. However, the next one, it needs to be to the right. That means this guy has to be a 0, and this guy has to be a 0 somehow. It's not divided by 0, but they have to be zeros. First, let's delete the 3 because we're just doing it from left to right. If I want to delete the 3 in particular, I have to, let's see, the only way I can turn that 3 into a 0 is if I add it by negative 3, which means I have to use my first row. So negative 3 of row 1 plus row 3, send that to row 3. It's R. So now I have 1, negative 2, 3, 1, 0, 1, negative 1, 3. And now this gets changed to a 0. If I multiply negative 2 times 3, that's negative 6 plus 2. That is going to be a, I believe it's a negative 6. This is negative 6. Oops. Yeah. So this negative 3 times negative 2, that's positive 6 plus 2. That's 8. And if I do it to the next one, negative 3 times 3, that is negative 9. Yeah, negative 9. Then negative 9 plus negative 5. Negative 9 plus negative 5. That's negative 14. And negative 1 times negative 3. So negative 3 plus 3, that's 0. Boom. So I have this. Now, my leading entries are still over here, but it's still not fully done. I deleted that first entry in row 3, but now I need to delete the second entry. It needs to be a 0. That 8 needs to be a 0. How can I get rid of that? Well, now some of you guys might have said multiply row 1 by positive 4. However, if you do that, you'll notice that this value will change because I'm multiplying this guy by 4 too. And then when I add that together, I will have a value. So I'm going backwards if I do that. There's an easier way to turn that into a 0 without worrying about that first equation or first row. If you instead multiply the second row by -8, then add it to row 3, and of course send it to row 3, then I still have this as 0, but I'll have this as 0 as well, because this is a 0, and if I multiply 0 times -8, it stays 0. So now I have 1, -2, 3, 1, 0, 1, -1, 3, 0, 0. That is -8. So this becomes 6. Yeah, it becomes 6. And then -24 plus that, that's, I want to say 24. -24, I'm sorry. Boom. Dun, 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 -8. Yep. So we have this matrix right here. So now if you look at our leading entry, boom, boom, boom. These all have to be a 1 now. They are to the right of each other, but I need them to be a 1. So the way I can deal with that is I can instantly do -1, 6 of row 3. Then I have 1, 2, 3, 1, 0, 1, -1, 3, 0, 0, 1, 4. So my leading entries are over here. 1, 1. They are all to the right of each other. And I'm going down, or to the right of each. But they're all leading coefficients of 1. And I have no row of 0, so I don't even have to worry about that. So this is in, or row echelon form. It's not fully reduced, but it is in row echelon form. It is in row echelon form, which means I can find the solution to it. So if I wanted to find the solution, I look at the last row. Notice the last row is, there's 3 variables, so x, y, and z. Z is equal to 4. Y minus z equals 3. And then x minus 2y plus 3z equals 1. And if I wanted to simplify all this, I have, what is that? Z equals 4. Y is equal to, if z is 4, that means I add 4 to both sides. Y is equal to 7 in particular. And then if I plug that in over here, I have x minus 7 to 7 plus 3 times 4 equals 1, which means I have x, what is that? Minus 2 equals 1. So x is equal to 3. So your solution is going to be 3, 7, 4. This ordered triple. Boom. So we're able to solve these systems. Now, next time I'm going to talk about reduced row echelon form and how we can actually put it in our calculator. That'll end for today, so I will catch you guys later. Take care. Bye.